Hello students, video D, lesson 19. We're going to do a confidence interval example for a mean. You know the theory, you know the ideas, now we need to change the formulas because we've changed the type of data that we're working with. Kim Shepard in the last video showed you how to grab that critical value T from the StatCrunch tool. And so we're just going to put it all together here. Computing a confidence interval for a population mean. Here's the example. Suppose 100 Cecil College students were recruited to take an IQ test. We'd like to determine if Cecil College students have a mean IQ that differs from the general population. So sample size is 100. The mean IQ in general is also 100. Those are just coincidentally the same. You can see it in your notes. It's probably not going to pick up with the lights on here. But here are the 100 IQ scores. There's 10 rows of 10 here, and you can see the first person was 107, second one was a 76, and so on. This is my sample of data. Remember, we're saying 2,800 students at Cecil College, so this is like a little piece of the pie. This is like 1/28 of the whole student population. I want to use that data to start making conclusions about the whole school. Okay? A statistician ran some summary statistics. You can see the pictures in your notes down at the bottom. Here's a histogram. Looks pretty unimodal, pretty symmetric. There does appear to be a little pileup of data right in here in that 80 to 90 bin, but I'm not going to get too bent out of shape about that. I mean, if I collected more data, I would guess this would continue to look pretty normal. I like to put some symbols here. Of course, we've got sample size n, 100 students. And this mean, this is the sample mean, y bar, 100.46. Now, of course, for the whole school, I would call that mean mu, and that's not 100. Remember, 100 is the population IQ mean score. For the whole school, that would be unknown. Mu equals, I guess, question mark. And here's my best guess for the standard deviation from the data, S. It was 15.9592. All right? And so you can see that. A couple of things I'm noting in my head. Think about those requirements. We're going to check them on the next page. But my sample size needs to be at least 30. I've got 100. Or my data needs to look pretty normal. The data looks pretty normal, and I have over 30, so I've sort of met the condition in both ways. I can meet it in one of two ways. I've got both. No problem there. All right, we feel even better about our data. Let's do it. Flip over to the next page, part A. To proceed with our confidence interval for the true average IQ at Cecil College, certain requirements must be met. Are they? And explain. Number one. What kind of variable am I working with? I'm working with a quantitative variable. It's IQ score, right? So that's the first thing we're always thinking about. Variable is quantitative, right? It's IQ score, and we're working with means. So we know we're not going to veer down this proportion path here. We're on the mean path. Number two, I need to presume that my data was collected unbiasedly, that my sample is random. I believe it says somewhere in there, it says 100 students were recruited. As long as this isn't like our nursing school or something like this, I just have to presume these are unbiased. I don't think it clearly says yes or no, but I will presume that the data is in fact unbiased. We have a random or semi-random or some sort of way to select students that wouldn't make the IQ artificially inflated or deflated. So we'll presume that's true. Number three, the old 10% condition, right? N equals 100, yes. So certainly N equals 100 is less than Cecil's population. It's less than 10% of Cecil's population. Yes, Who knows the exact number, but about 2,800 students or so. So that's certainly less than 10%. So we're good there. Last but not least, don't you dare tell me successes and failures I got 10 and 10. You'd be in big trouble. This is a quantitative problem. We're working with means. And so n definitely exceeds 30. That's the magic number for means. Check. PS. Data also looks normal. Check that one off the list as well. I don't need both, I just need one, but I just happen to have both. So we're doubly covered. Everything seems good. We can proceed with inference. We can do the interval. All right. Part B says how many degrees of freedom and determine the critical t value. All right, make some space. Flip the slide. How many degrees of freedom determine the critical t? Here's what I'm going to do. I'm going to trust that you're going to go to StatCrunch and go dig this up and practice. Critical t comes from StatCrunch. You have to use that t calculator. All right, how many degrees of freedom? Sample size was 100. You can check me on your TI calculator. 100 minus 1 is going to be 99. I guarantee it. So we've got 99 degrees of freedom. Put this picture in your notes. Just because you can do it on StatCrunch doesn't mean you might never want to look up what the picture might look like. So put this in your notes. And we're doing 95% confidence. So here's 95% in the middle. And this is a t model with degrees of freedom of 99. And we've used up 95% of the area. I've got 5% left over, chopped in half. Up here should be 0.025. Down here, same thing, 0.025. T models are centered at 0. Here's the negative t number. Here is the positive t number. And why do we need this number? Well, I'm going to be doing y bar plus or minus t times s over root n. And this, we need that one. That's what we're doing here. All right? So pause the video, go get that number. Critical t, use the t calculator, and when you come back, what is it? Well, it's 1.984. There, 1.984. That one's negative, 1.984 there. And you're thinking to yourself, if I did a z incorrectly, isn't that 1.96? And yes, remember 1.96 for z? This was Gossett's discovery. You could see with big sample sizes, like 100 data points. The difference between a 1.96 standard error is, here's my interval, and now I go 1.984 standard. I guess we're here, right? It goes out a little bit there. But this is the right answer. Statistically, we just can't say, well, the heck with it, I'm going to use 1.96. Close enough. Not in our classes, you don't. This is the number that we've got to use. All right, let's do the formula. Down at the bottom, part C, calculate the interval. All right, this. Hey, the formula is right here, students. How about I'll put the numbers up top, and then that's the formula that I'm using. The numbers are coming from the table on the first page. You can see the summary statistics at the bottom. And so y bar. Our sample mean was 100.46 plus or minus. Now right away, say students, does this seem like any evidence that Cecil College students differ from the general pop? Right? The sample was about a half point higher. I mean, are you convinced we're smarter than average here? I'm not sure, right? This is pretty darn close to 100, which makes sense to me. So we'll keep that in the back of our minds. The t number, plus or minus 1.984, right? I hope. Yes. And then the standard deviation comes from the summary statistics. It was 15.959. The sample size was 100. Make sure you don't put 99 there. It's the full 100. These are easy. This is easy stuff. Just carry this one down. Put 100.46 here. Plus or minus, clean this left or the right hand side up. So this is your margin of error, and that will be about 3.166. Best guess, plus minus, margin of error. Your margin of error is based on three things, right? This is your standard error here, and this is based on your confidence level, how confident that you want to be. So we're jumping out 1.984 standard errors. That's the margin of error. Subtract first, put the smaller number first, or you'll be in big trouble. So 100.46 minus takes me down to 294. 100.46 plus takes me up to 103.626. Well, I just can't contain. I have to say this. This is IQ points, right? This is not percentages. I know everything's been percentages in all those proportion chapters that we've been working on. This is IQ points. So don't you dare put 97.294% and 103%. And I only say it because I've seen hundreds of students do it in the past. So this is not a percentage. Part D, on the back, interpret your interval with the sentence in context. Well, there's the interval, and it's IQ points again. So here's what we're going to say. We are 95% confident that the interval, this one here, right? I'll even write it just 97.294 to 103.626 contains the true mean IQ score for all Cecil College students. We are 95% confident that the interval here, the 97.294 up to 103.626, contains the true mean IQ score for all Cecil College students. It's one word that's got to be in there. We're doing a confidence interval for a mean. So don't skip that word. That needs to be in there for sure. Okay? And I don't know, part E feels like it's going to be, do we have any evidence that Cecil differs from the general population? So let's see if I like the way that I think here. I do like the way that I think. Part E. Do we have any statistical evidence that Cecil College students' IQs differ from the generally agreed upon average of 100 points, and why? We've done plenty of these in the past just for IQ, or for proportions. In or out? Is the 100 in or out of the interval? Right? It's clearly in. And so, since an IQ of equal to 100 is inside the interval, there's no statistical evidence that Cecil students differ from the general population. Since IQ equals 100 is inside the interval, there is no statistical evidence that Cecil College students differ from the general population. No better, no worse. That makes sense to me, I think. Since the IQ equals 100 is inside the interval, there's no statistical evidence. Cecil students differ. What would I need to convince me that we're smarter than average? the whole interval there would need to be above 100, right? Then statistically speaking, we would have some evidence that at Cecil our IQs are higher on average than the general population. What if the opposite happens? If the whole interval was in the 90s or 80s or something, then I would have evidence that the average IQ here at Cecil is below average. You got to remember, the sample mean Y bar was what? Is it 100.54? Got to double check that. I think that's it. 46, excuse me, 100.46. And by now we have a sense of these things, though we still need to run the test. It's awfully close to 100. Like, who's really going to be convinced that this is telling us that we're smarter than average just because this is a tick above 100? All right, we know better by now. All right, one part at the bottom, I believe, part F. Yes, what's the margin of error? What factors are influencing its value? And just think about this for a minute or two. All right, for means, margin of error is all that stuff to the right of the plus minus. It's the t number times s over root n. And boy, there's three numbers here, so I'm guessing those might be the three things that are influencing the value of margin of error. From this problem, it was 3.166 IQ points. And I don't know which one we want to start with, but let's think about it. I guess we'll just start with t. Certainly, t is influencing margin of error's value, and t is based on what? T is based on confidence level. Pick up sample size here in just a second. But t is based on confidence level, and as I think we know by now, the more confident that we need to be, if I need to be more confident of hitting the target, I would crank up t, right? Instead of 95% confident, I'd be 99, and that's going to happen. So the more confident we need to be, t definitely increases. What else is affecting margin of error? Well, let's do sample size next. So clearly sample size. It is in the denominator. So the bigger sample size gets, the smaller margin of error gets. And so all these ideas hold from the earlier lessons. Sample size. As n increases, margin of error decreases. Right? More data means a more accurate interval is going to tighten up. Last but not least, let's spend 1 minute talking about S. S is the standard deviation. S is the standard deviation from the data. And don't tell me this one, I've heard it before. Well, if I want to get margin of error down, I just need to decrease S. I can't change the data. If there's lots of variation in my data, then S will be big, and our margin of error will be big. That makes sense. If you have lots of variation in a data set, shouldn't my confidence interval be wider because I'm less sure about the true values? So I can't change this one. These two, I suppose I could fiddle with to my heart's desire and change them if I need to be less confident. I could collect more data. This one I can't change. Standard deviation from the data, we can't change it. But we do need to be aware that as S increases, more variation, margin of error also will increase. Bigger intervals, wider intervals. All right. My camera woman's standing up. That's signaling me that we're all out of time this time here. So, yeah, that's it. Thanks for watching. A couple more examples to go. We'll see you in class.